All right, all right. Hi, everyone. Happy to be back at PyCon APAC. And welcome to my talk on optimizing dependency management and deployment for serverless Python applications with UV and PANTS. And I don't know about you guys, but I love AWS Lambda with Python. I've worked with this pieces of technology for several years now, and I've seen its strengths, I've seen its weaknesses, and I've seen some pain points along the way. And for today's presentation, I would love to share to you some investigations we had on how to alleviate some of those pain points in packaging Python for AWS Lambda. So first off, a bit about myself. Hi, I'm Arnel Sarmiento. You can call me Nel. I'm from Davao City, Philippines. I'm a Python backend engineer at Elementa. We're a fintech company based in Sydney that builds tooling for financial advisors. I'm also AWS certified with the AWS Cloud Practitioner and the Solutions Architect Associate certification. And I'm also the community lead of Durian Pi, Davao's Python user group. So in Durian Pi, we do conferences, workshops, and monthly meetups. So if ever you're in Davao City, feel free to hit me up. Maybe you can join a meetup just around the corner. So for this talk, I'm going to share some challenges in deploying serverless Python applications. We're gonna walk through optimizing dependency management with the PANTS build system. We're gonna see how we can deploy those optimized Lambda function zip files with Terraform and how we can speed up the installation of our packages with UV. We're gonna look into some caveats, best practices, and some use cases. So, to first introduce to you AWS Lambda. AWS Lambda is a serverless compute service that automatically runs your code and scales according to your needs. It can be a short snippet of code or entire application inside of AWS Lambda as long as it fits. And it automatically scales for your workload and you will only be charged for your usage. So that's AWS Lambda. So what we see here is that the provisioning of our infrastructure is handed over to our cloud service provider. And all we have to focus now is worrying about our business logic, the differentiated work to say. And while we can scale to theoretical infinity, we can also scale to zero. So essentially, if you don't have any users, serverless will essentially charge you $0 for your cloud provider bill. So that's awesome, right? So that begs the question, how do we build Lambda functions with Python? So I'm gonna show you some pieces of code. This is like a small Lambda function. This is our whole Lambda handler file. It uses a Pydantic model, and we have a requirements file for Pydantic. So that's our whole file system, our function, and just a requirements file. So how do we do this? Usually we do a shell script like this under the hood. We have our entire Python code instantiated to a repository, to a single directory, and we install all of our pip requirements in that directory. After which we zip that entire directory and then upload that to AWS Lambda. All right, sounds good, right? However, you might encounter something like this. Pydantic core, no module named. Why? We already installed Pydantic. Why do we get this error? So if you look at PyPI and you look at the downloads folder, you see that there are several versions for this message spec library. So message spec is like a schema validation tool similar to Pydantic. If you see, there's a version for Mac OS with x86, Mac OS with ARM, Windows, Linux, for different types of CPU architectures. So this type of discrepancy occurs wherein the computer that we used for building our Lambda function misaligns with the target architecture. So what happens there is that we're building locally with a MacBook, for example, a Mac OS ARM, and it doesn't work with our target Lambda function, which is a Linux x86 compute. So that's the type of discrepancy that occurs. And we can usually fix that if we add this line of code here. So you just dictate what platform we want to add for our pip install. And just like that, we have a working Lambda function. All right. And you can also do something like this. You can emulate the CPU and the operating system with Docker, and all is good. And that's how we build a Lambda function. All of the current infrastructure as code tools, CDK, Terraform, SST, SAM, whatever it is, that is what happens under the hood. Just Python, pip install into directory, and you zip it and upload it to AWS Lambda. It's that. It's just like that. All right. So that's the current workflow. What's the problem? All right. Where does the pain points occur? So the pain points occur when we encounter things in multi-function projects. So for example, we have this function that has Pydantic as a dependency and another function that has Pydantic and request as a dependency. So one really good way to manage the size of our Lambda functions is to have a separate requirements file for each Lambda function, just like that. However, there's this thing that occurs when you're dealing with dozens of Lambda functions needing their own requirements files. So you have to manage the requirements for each requirements file. Sometimes you forget, and sometimes you're shocked. Oh, why doesn't this work? Oh, I just forgot to put this requirement to the file. All right. So you really have to rely on human memory for this, which is not a really fun way to handle our dependencies. Another issue occurs when we're building our dependencies, our code artifacts, step by step. So in our infrastructure as code tools, each Lambda function dependency will be packaged one by one. One virtual machine will be instantiated, it will install that, and after it's installed, it will instantiate another virtual machine, even if you have the same exact requirements for each Lambda function requirement. So it takes a lot of time, especially when you have dozens of requirements files for dozens and dozens of Lambda functions. And it could take eternity, essentially. So that's two of the problems. Another one final problem that we can encounter, a few pain points, is code sharing. So let's say, for example, that you have two Lambda functions that want to share this piece of code, just a logger, essentially. So the most common best practice way to do it is upload that shared utility function into a private pip repository in, let's say, AWS code artifact. And then, since it's now in our private pip repository, we can just add it in the requirements file with pip install. But the same issue occurs. So, dozens of Lambda functions, dozens of requirement files, and step-by-step building. So that's the issue. So we've been looking for solutions. So we've been looking to how can we optimize this entire workflow. And some requirements that we want to take into account is it has to, number one, handle cross-platform. It has to be fast. The builds have to be fast to fix our problems. And it has to enable code sharing. So we explored a few solutions, and the one that we settled with is the Pants build system. So the Pants build system is a fast and scalable user-friendly build system for code bases of all sizes. It could be a monorepo, or it could be just a small repository. So one of the key features that I love about the Pants build system is, number one, it has dependency inference. What does that mean? It means that for each of your Lambda functions, each of the files in your handler, it will inspect the imports of those functions, and it will only include the files that are included in the imports in the overall artifact, the overall zip file. So you don't have to specify what files are included. It will infer that automatically for you. Another one is that it automatically handles cross-platform builds with PEX. It handles parallel builds and cache builds. So let's see that in action. So here's what Pants repository looks like. Lots of files. So let's break this down. First, we have our first Lambda function, which is just this one. We have a second Lambda function, which has requests and a shared models weather response model. So if we look into the shared models folder, that's where those models reside. That's where we pull them from. So we have that shared folder. And the main configuration component for Pants is this pants.toml file. So the important part of this is that we have the Python and AWS Lambda Python backend, which allows us to build Python Lambda functions to the build system. And here in the build file in our source directory, we have specified where does the Lambda function reside and what is the name of the Lambda function handler. So we specify those for each of our Lambda functions. And all we have to do is run pants package colon colon. So colon colon means you package for the entire repository. So let's see that in action. So here we run a pants package. And as you can see, it runs two functions in parallel. So we see that for the first function, it built with requirements of Lambda power tools and Pydantic. And for the second function, it's Pydantic and requests. And if we look into our folders, into the dist, we see that those Lambda functions are now packaged instantaneously, just like that, in parallel. If we look at the user Lambda function, we have power tools installed right there. We have Pydantic there. If we look into our user handler function, you see that we have the user shared models. And if you see at the user shared models, that is the only file that was imported because that was the only file that we needed. And it automatically inferred that in our function file. And same goes with our weather function. There's only Pydantic and requests. And if we look at our Lambda function, we have the weather response. And if we look at our shared models, we only imported weather.py, only the things that we needed. All right. So those are some incredible things that we can do with the pants build system. And to continue with this, if we run pants package again, it's going to do that instantaneously. And because it cached all of our zip files for us. So we don't have to do unnecessary builds if there aren't really any code changes. So that's awesome. So that's what we've seen here. For Lambda function 1, let's say we did 5 seconds or 9 seconds. But for the second, with the same version, second build with the same version, we did 0 seconds because all of it is cached for us. So let's try to make some changes. Let's say in our user handler file, instead of we say hello world, we say hello PyCon APAC 2025. All right. And if we run pants package again, it will only build one Lambda function there. So what you see there is that since only one file has changed, only that file will be built. We will not have to do unnecessary compute when it is not needed if there are no functions that have changed. So that's awesome. So now that we have our zip files optimized, all of it is under the most minimum amount of files that are needed, we can now use Terraform to essentially reference our zip files in our dist repository and then specify our Lambda function with that configuration for both of our functions. You see there we have our dist files, just like that. And then, if we run Terraform apply in our Terraform directory, it's going to essentially deploy our Lambda functions for us. We enter yes. Just wait for a bit. It's gonna take around 5 seconds. More than 5 seconds. And just like that, our Lambda functions are now uploaded to AWS. So that's the entire workflow. We build all of our zip files individually in parallel with the pants build system. We reference those zip files in Terraform and upload those to AWS Lambda. So we have demonstrated these capabilities of the pants build system. However, these capabilities are only for the build step of our whole application development cycle. We can still do better. We can add another step for our development cycle. So let me introduce to you UV. So UV is a drop-in replacement for pip that promises 10 to 100 times faster install times. So what you see here is that we have a pyproject.toml file, which is essentially a requirements file that specifies all of the requirements, the dependencies that we need for our entire project. So that's just one requirements file defined for the whole project. We don't have to define a single requirements file for each of our functions. That's for the entire project. So that's centrally managed. And for us to integrate UV with the pants build system, we can just reference where our PyProject.toml file is, and we can do something like this. So to demonstrate the power of UV, let me first demonstrate how the lack of capability of pip, let's say. So let me demonstrate this. So we're gonna instantiate our virtual environment. We're gonna activate it. And then let's look into our requirements file. So we have these requirements, and then let's do a pip install. So again, it's gonna take a while. So it's still looking at our cache directories. It's not even starting to download yet. Yeah, let's just wait a minute. All right, so it's now starting to download. Finally, it's downloading requests, Lambda Power Tools, MyPy, Botocore, everything that we need. So it's a bit slow to say. All right, so I think we're done. We're done. So that's pip. How does it look like when we run UV for installing? So it's something like this. We create a virtual environment using UV VNV, and we have our virtual environment in our code. We then activate it, source, something like that. And then to install all of our dependencies, we run UV sync. And we're done. That's the power of UV. That's the performance benefits that we are seeing when we're installing our dependencies. So that's the whole workflow of this entire stack. So we defined one requirements file for our entire project. We will install that locally for our local tests, local builds with UV, with blazingly fast speeds. And we can use that to iterate our whole application locally. And for our build time, we will run parallel builds with the pants build system with dependency inference, all based from that centralized PyProject.toml file. And all of that will be deployed for AWS Lambda with Terraform. So that's the whole system. Terraform can actually be substituted with other infrastructure as code tools that supports uploading a zip file to AWS Lambda. So it can be CDK or any other IAC tool that you want. So that's it. Some caveats of this workflow. It could be, there's a steep learning curve when you run UV and the pants build system. It might be a bit overkill, especially for smaller repositories when you have just 2 Lambda functions and you can handle managing those requirements files yourself. And it's not really ideal for teams that don't have a DevOps culture in place. So a team might not be used to build automation, testing, linting, things like that, and structured dependency management. So they might struggle in that regard when adopting this tech stack. By the way, I don't have a name for this whole stack yet, but I'm just gonna propose put. So yeah, let me know if you have any other suggestions. But yeah, that's pretty much it for my talk. Here are my socials. Feel free to reach out to me. Here's a QR code if you want to scan. And thank you. So I'll give you a few seconds to scan. Yeah, and also want to plug, in Duriyabtai, we also launched our official website much recently. So you can reach out to us at durianpie.org. And huge shout out to all of the developers that helped us in building this website in time for PyCon APAC. And thank you.